Good morning, students. We are learning predicate calculus, and the topic to discuss is this is done. All right. The topic to discuss is transformation of a formula into Pnf normal form, Pnf. A formula is said to be in closed form if all the variables appearing in it are quantified and there are no free variables. When do you call a variable free variable and when do you call it a quantified variable? Well, when there is a quantifier, what are the quantifiers? There are two quantifiers, for all and there exist. These are the two quantifiers. When it is said that for all x, it implies that whatever x refer to, that entity is taken into account in its uh, form where all the subentities of it, satisfy the rule or any um, statement that is described for it. That is for all x. When I say for all x, x uh, x is, for example, ice cream. When x is ice cream, I can say for all x, where x is ice cream, x is sweet and x is sweet. All ice creams are sweet. For instance, if here we talk in terms of for all quantifier, it implies to all the ice creams, any flavor, any company, any type. Let us take example of there exist x. When it is said that x, there exists x, x is referring to some entity, then here it implies that some x means there is one particular x or few particular x, but it's not all x. If it is considered that x is a uh, mm, let us take example of chocolate. Okay, x is a chocolate, and there exists an x which is not sweet. X is not sweet. This statement implies that apparently there are few or one um, X values, instances of X that do not that is not sweet. It does not imply to all the chocolates. Here in this example, it implies to all the ice creams. Whenever a variable is preceded by for all or there exist, it is said to be quantified. All right, it is said to be quantified. When there is no quantifier associated with a variable, it is said to be free variable. Free. What is pre-next normal form? A closed formula alpha in first order logic is said to be in pre-next normal form if and only if alpha is represented as q1 x1, q2 x2, where qk are quantifiers which are for all or there exist, xk are variables. What do you understand from this? With every variable, there must be a quantifier for k greater or equal to 1 and less than or equal to m, while m is a formula free from quantifiers. This pre-next normal form has got two parts. The first part corresponds to the quantified variables. The next one is uh, a formula free from quantifier. The list of quantifiers is called prefix and M is called the matrix of the formula. As said, there are two parts. First part belongs to the quantified variable and the second one belongs to the formula. The first part, which are list of quantifiers, is called prefix, and the second one, which is a formula, is known as the matrix of a formula. And M is assumed to be represented in CNF. What is CNF? Conjunctive normal form. We already learned a conjunctive normal form. The formula M is in CNF notation. For example, there exists X for all Y, P of X or Q of X comma Y. This is in Pnf notation. What is Pnf notation? Pre-next normal form. And how do you write formulas in Pnf notation? You have got two parts. The first one um, corresponding to quantified variable and the second one to the formula. Formula must be in CNF form. The example is there exists X. This is a quantified variable. For all Y, this again a quantified variable. Which is a variable and which is a quantifier? There exist, and for all are quantifiers. X and Y are the variables. P of X or Q of X comma Y this part is M, which is the formula, which is in CNF form. This example, which has got P of x implies there exists y, Q of x comma y. Is this in Pnf notation, Pnf form? Well, this is not in Pnf form. Why? Because it is not satisfying the criteria. What is the criteria? Well, the criteria is uh, to have a quantified variables followed by the formula in CNF form. All right, this is pre-next normal form. Conversion of a formula into Pnf notation. When a formula is not in Pnf notation, it can be converted into Pnf notation. How can it be converted into Pnf notation? Well, by uh, applying these equivalence laws. This alpha, FOL formula alpha without a variable x. Alpha of x means FOL formula alpha which contains a variable x. Q is quantifier for all or there exist. These equivalence laws, there are 4 in number. Here Q x alpha x into B. How can this be written as Qx in parenthesis? In another parenthesis, alpha of x asterisk B. This symbol asterisk represent and or. Essentially, here it means that when you have got a quantified variable and a formula with and or symbols, instead of putting and or, asterisk is placed here. Asterisk beta. If you observe, this is not within parenthesis. In equivalence law, this can also be converted into a parenthesized statement. This is law 1. Moving on to law 2, alpha asterisk qx. Q is a quantifier, x is a variable, beta x. How can this be rewritten into something that is valid in PNF, pre-next normal form? How is that done? This qx is quantified variable. This is taken out and placed in the beginning. Qx. Then we have got alpha asterisk beta of x. This one is equivalent to having alpha asterisk q of x, where quantified variable is in between two other entities. Law number 3. It states that if there is a statement like not for all x alpha of x, this can be equally uh, written as if there is not placed before for all, it gets converted into there exist. There exist x is not when applied to for all x would convert for all x into there exist x within parentheses, and this not can be placed with alpha and can be parenthesized. So we get uh, not alpha of x. This one is the equivalent form to this, the first one. Going ahead to the next law, which is law number 4. Um, Here both the laws are very much similar. What you find the difference is instead of for all, here is there exist. When not is applied to there exist, it turns out to be for all. For all x and not is placed before this alpha, you get alpha x of uh, alpha of x. These are the equivalence laws which are useful for the conversion of a formula which is not in Pnf, which is pre-next normal form, to pre-next normal form. Is it clear? Prove the last equivalence for the sake of clarity. This last equivalence law can be proved, which is specified here. This is the law, and the proof is let I be any interpretation over the domain D. We are having domain, and there is interpretation given over the domain. And to prove these are equivalent, we need to prove that not of there exists x alpha of x is true if and only if for all x not of alpha x is true under any interpretation I over any domain D. Look here, domain is a set of values and interpretation is using the values uh, to realize whether uh, it is leading to true or false statements. If it is leading to true statement, it essentially means that it is true that in that particular interpretation over that particular domain is true. Let us assume this statement is true under I over D. Prove that is also true under I over D. Since not of there exists x into x of or alpha of x is true, it is assumption. We are assuming that for a particular domain, there is an interpretation of the statement or a formula, and it is assumed to be true, which implies that there does not exist any x for which alpha of x is true. That is, for all x, alpha of x is false. And this proves that for all x, alpha of x is equals to false. That is, for all x, not of alpha of x is true. Finally, it is said that for all alpha, not of alpha of x is equals to true. Through this, it is proved that those two statements of formulas are equivalent. When for all x, alpha of x is false, then for all x, not alpha of x is true. When this is false, not alpha of x is true. Because not alpha of x is true, eventually we get the whole formula to be true. Law for the equivalent laws, for all x, alpha of x, and for all x, beta of x. This is equal to for all x, alpha of x, and beta of x. This is too obvious. We know that for all x, this can be taken as common in this formula, and you can place there is no need of for all x again, as it is taken as a common, and placing this alpha of x and beta of x within parentheses and having and symbol as it is makes these two formulas equivalent. Likewise, instead of for all, when there exists x appears in the formula, again there exists can be taken out and can be used as a common statement for this formula, and this formula can be parenthesized as alpha of x or beta of x. Quantifiers for all and there exist may be distributed over and or. However, they cannot be distributed over or and. Look at this example. For all x, here you see there is or. For or, this statement, this formula cannot make for all x as common. It is said that it can be distributed over and followed by or, but it's not for or followed by and. Here there is all right. It's not followed by. It's for all. For all. For and corresponding to and statement, there exist for all or statement. Please try to understand this again. For all quantifier may be distributed over and operator, but not for or operator. For all cannot be distributed over or. There exist can be distributed over or, but not for and. That is shown here. For all x, and there is an or symbol, and this cannot be taken out and placed here in this form. This is not equal. Both are not equal because there is an or symbol. And for all quantifier cannot be distributed over or symbol. There exists a quantifier cannot be uh, distributed over and operator, but it can be for or. Observe here there exists x is followed by a formula that contains OR. For all x is followed by a formula that contains AND. Is it clear, students? All right. Let us discuss this example. Show that there exists x, p of x, and there exists x, q of x is not equal to there exists x, p of x, and q of x under the following interpretation. When you talk about interpretation, there are some values specified. For domain, values specified are 1 and 2. P of 1 is equals to true, P of 2 is equals to false. Q of 1 equal to false and Q of 2 equal to true. These are the specific values for to understand the um, inequality of these two formulas. The solution is we can easily see that the formula there exists x p of x and there exists x q of x is true. This is true under the interpretation I. Whereas under the interpretation I means what? Take for example d equal to 1. When we are taking d equal to 1, x is 1. P of x is true. Q of x is Q of x is false. Then how can this statement be true? There exists x p of x and there exists x q of x. All right, here this is one statement, one formula. There exists x p of x. There exists x p of x means there is some value in the domain for which p of that value is true. This is true because there exists one where p of 1 equal to true. And this is another formula. There exists x, q of x is true. When values are taken into account, here in this case 2 has to be considered because for 2, q of 2 is true. And because we have found true and true for both, when x is 1, this statement is true. When x is true, second statement or formula is true. When both are true, it is joined by and, therefore, the whole formula is true. This one is true. Whereas, for all x, p of x and q of x is false. How it is false? When x is chosen to be 1, p of x is true, q of x is false. This evaluates to false. If x is chosen to be 2, p of x is false, q of x is true, which evaluates to false. And therefore, the whole formula evaluates to false. And um, here it is proved that this formula is not equal to this formula. Similarly, for all x, alpha of x, or for all x, beta of x is not equal to for all x, alpha of x or beta of x. You please substitute the values and check whether we could satisfy these this formula under a particular interpretation. Take values 1, substitute and see. The next topic is the conversion of Pnf to its standard form, which is known as scolemization. Scolemization is uh, a form, a standard form, or a special form uh, into which Pnf needs to be converted. What is Pnf? Pnf is Prenex normal form. Prenex normal form. This Prenex normal form can be transformed into a special form called scolemization or standard form. And what is the need of having this Pnf converted into scolemization? Uh, it is needed in the resolution process. The process of eliminating existential quantifier from the prenex of the Pnf notation and replacing the corresponding variable by a constant or a function is called scolemization. Such a constant or a function is called scolem constant or scolem function. We have got there exists x, that is existential quantifier. This has to be eliminated in the sense that they have to be removed from the formula. And when you are removing there exists existential quantifier from the formula, this has to be replaced by a constant such as x or y, or it can be replaced by a function alpha of x. All right, by a constant or a function. Replacing existential quantifier by a constant or a function is known as scolemization, and whatever is being used for this replacement is known as scolem constant or a scolem function. X and y are known as scolem constant. If a function is used, it is known as scolem function. And what is the procedure? Well, the procedure is described as shown. Let Q1 x1, Q2 x2, and so on up to Qn xn, followed by m, be the Pnf notation corresponding to some formula where Q1 x1, Q2 x2, and Qn xn is representing the prefix and m is the matrix. The steps that are needed to be followed in the uh, scolemization procedure are these. This is 1, this is 2, this is 1a, this is 1b. Scan prefix from left to right till we obtain the first existential quantifier. If Q1 is the first existential quantifier, then choose a new constant, C, which should not belong to the set of constants in M. M is matrix, which is which follows the prefix. There should be no constant chosen from M to be replaced for the existential quantifier. Replace all occurrences of x1 appear in M by C and delete q1 x1 from the prefix. If qr is the first existential quantifier and q1 up to qr minus 1 are universal quantifiers appearing before qr, then choose a new r minus 1 place function symbol f which does not belong to the set of functions appearing in M. Replace all the occurrences of xr in M by like this f of x1, x2 up to xr minus 1 and remove qr xr from the prefix. Here, when there is a first existential quantifier qr and q1 to qr minus 1 are universal quantifiers like this 1, 2, 3, 4. This fourth one is existential. These first three are universal. Then what has to be chosen? A new r minus 1 place function symbol. One function symbol has to be chosen that does not occur in M. Replace that x of r means with quantifier qr there is xr, right? So xr has to be replaced in M by this f of 1, 2, 3 and then remove q of qrx xr. That is the first step. The second step is repeat the process till all existential quantifiers are removed. The first step has to be repeated until all the existential quantifiers are removed. All right, after the removal of that, the standard form can be expressed as for all x1 up to for all xp, c1 and cm, where each ck is a formula in disjunctive normal form. Will you tell me what is CNF and what is DNF? Conjunctive normal form and disjunctive normal form. All right. Ponder over that and try to learn if you don't remember. That is about a scholemization procedure. This one we will study tomorrow. Clauses in FOL and followed by resolution refutation method in FOL. First we'll look at clauses, then resolution refutation. All right, students.